Hello, this is Jack Jackson. In this video, we will learn how to construct a confidence interval for the difference in two means from two independent samples. In other words, a two-sample t interval. In the last video, we looked at what happens if you had paired data, like before and after data. That was not truly two samples. They were dependent. They were paired or matched sets. What we really had was one sample of ordered pairs. What we have in this situation, in this video, however, is a little different. So we want to develop a method for computing a t-interval estimate for the difference in means of two independent samples. We'll use these methods when we have two samples which we have reason to believe are independent. We'll develop these using a t-distribution. There is a z-distribution version of this, but the t-test is much more realistic, so I'm just going to go over that method here. So first, let's review a couple of things. Recall that with any two distributions, the individual measurements, their differences have a distribution as well. The mean of the distribution of differences is the difference in the means of each distribution. For example, mu of y minus x mean is just mu of y minus mu of x. Furthermore, if the two distributions are independent, then the variance of the distributions is the sum of the variances of the individuals. However, this doesn't mean you can add up the standard deviations. So the standard deviation of y minus x then turns out to be the standard deviation of the x squared plus the standard deviation of the y squared, and then add them up and then square root. Notice even whether this is a plus or minus, this is a plus. This requires independence. And furthermore, if two random variables are distributed normally, then their difference is distributed normally as well. So those are important things in the background that's going on to help us out. So let's just kind of put that to work and make sure we got this. And so this, if we have two independent samples, sample 1 has size n1, sample 2 has size n2. The mean of sample 1 is mu1, let's say the population it comes from. The population that sample 2 comes from has mu2. Then the difference would have a mean of mu1 minus mu2, if we subtract in that order, sample 1 minus sample 2. And the standard deviations are sigma 1 and sigma 2, respectively. And so that would be square root of sigma 1 squared plus sigma 2 squared. Square them, add, then square root for the standard deviation of the difference. So the standard error, okay, or the standard deviation of the x bar 1 minus x bar 2 turns out to be the sigma of the first one squared divided by its sample size, n, and this plus the sigma of the second one squared divided by its sample size, so that's n2, and then add them up and square root. Of course, we're assuming at this point that we don't know sigmas. But we do know sample standard deviation. So we just replace the sigmas by the s's, and that's at least approximately the standard deviation of the difference in x bar values. So I'm going to call that the s sub d. That's the standard deviation of the samples differences. And it is given by this formula, s sub 1 squared over n1 plus s sub 2 squared over n2, and then square root. All right, now if we consider the distribution of differences between the sample means from two independent samples, we see that the test statistic t star has a t-distribution with degrees of freedom given by this kind of more complicated formula. T star is just this difference minus the mu of the differences over the standard deviation of the differences. And d is given as x bar 1 minus x bar 2. Mu sub d is mu1 minus mu2. S sub d is the formula we just worked out, s1 squared over n plus s2 squared over n2, and add those up and take square root. The degrees of freedom has this rather complicated looking formula here. I'm not going to bother reading it to you. There it is on the screen. And see, these are formulas for what's called the non-pooled estimates of standard deviation of the differences. we do not assume that the standard deviations are the same in these two samples, and so we can use this formula. This degrees of freedom may not be a whole number like it was before. Now there's another version of this. If we can reasonably assume that the two independent samples come from distributions with the same standard deviation, then we can get slightly better results by using a formula for the standard deviation of the sample means, which basically considers the data as one big sample when computing the sample standard deviation. The formula for the standard deviation is given above. Okay, unfortunately, this formula is more complicated than the corresponding one for the non-pooled method. But fortunately, the formula for the degrees of freedom is much easier than the pooled version. It's just sample size n1 plus sample size n2, and then subtract 2. Okay, so we can use one of these sets of formulas or the other. Now, in my class, we will not be using the pooled version. We will always be using the non-pooled version, but it does have certain advantages in certain situations. Now, here's the good news. Unless you're very certain that the standard deviations of the populations from which the two samples are drawn are the same, I would say that's rarely true, you should use the non-pooled formulas. In my classes, we will always use non-pooled versions. Fortunately, in my classes, we will never have to know either set of these formulas since they are already built into the graphing calculators. So, yeah, you saw those nasty looking formulas? Don't worry about it. We don't have to know them. There's also a two independent sample z-test as well. However, it requires that you know the population standard deviation of each sample, which is quite rare. So I don't think I gave you any homework problems about that. But these are also built in the calculator. So there are also options for a pooled two-sample t interval and a two-sample z interval, but we will not be using them. So in my classes, we will always use the non-pooled t-interval when we want to compute a confidence interval for difference in means of two populations from which we have drawn two independent samples. And we will always use the built-in TI calculator apps to perform these calculations. In other words, we will always use a two-sample t-interval on the calculator in this case. Once you got that, it's pretty easy. Watch. Here's an example. A study was designed to estimate the difference in diastolic blood pressure reading between men and women. The following measurements were taken. Construct a 99% confidence interval for the difference, men minus women, and diastolic blood pressure. So obviously, these are not before and after or paired data from the same people. They don't have the same sample sizes for the two groups. That's okay. It doesn't bother us. But we have two data sets. These are independent from each other. We would assume, and so we will treat this as two independent samples. So our interval is going to be on the difference in the means, and we have to decide which one is group 1 and which one's group 2. It really doesn't matter. We just have to know how it is to interpret. So let's say the men be group 1 and the women group 2. I think that's the way I've got it set up at this particular time. Could have been just as easily the other way around. So I put the men's data in L1 and the women's data in L2 right here, or in a spreadsheet over here on the Inspire where it's actually just labeled it men and women, and then difference right here. Okay, and the difference is group 1 minus group 2. Okay, so the difference will be men minus women. So if it comes out to be a positive difference, that means men have a higher blood pressure. If it's negative, it means women have the higher blood pressure. Okay, so our stuff is data, so we do a two-sample t-interval. So click on Stat, go down to number, turns out to be 0 down here, two-sample t-interval. We're going to do an interval, and it's two-sample, has the stuff we need for t. So select data. List 1 is L1, list 2 is L2. So that's data set 1, data set 2, both frequency 1. We want a 99% confidence interval. So that's confidence level is 0.99. This has no or yes here. We're going to choose no. It's blacked out right now, but that's no. Hit that. and then go down right under that. There's this thing that says calculate. So click on that and calculate it. And look at that. Just like that, it returns the two means of the two samples and the standard deviations and the two sample sizes. So it says the mean of the men was 77.375 and diastolic blood pressure with the standard deviation of about 8.35 from our sample of size 16. For our sample of size 13 women, we got a mean blood pressure of 71.1, let's say, and a standard deviation about 9.2. But most importantly, it returns the actual confidence interval for us. It does the whole thing, and we don't have to do hardly anything. Just know that this is the right one to do. Type in our data, press a couple buttons, and we got it. So this gives us the confidence interval of negative 2.918 to 15.514. So whatever units we're using here that the blood pressure is measured in, we're saying that we're 99% sure that the difference between men minus women in that order is somewhere between negative 3 and 16, let's say. Rounding those off a little bit. So here's kind of a summary. The diastolic pressure, we have the sample size, the mean, and the standard deviation. Put that together in a table for men and women. And you can see those numbers there with all the digits displayed by your calculator. A 99% confidence interval for the difference, men minus women in diastolic pressure is that. So notice the confidence interval is for the difference in values, not for, say just men or just women or even together. Now, since 0 is in the interval, we cannot definitely conclude that the men will have a higher diastolic blood pressure on average. Even though they did in the sample, we're 99% sure that the true mean is somewhere between negative 3 and 16, but 0 is in there, so there may be no difference at all. A two-sample t-interval exercise. Here's one more exercise for you. This time it's given with summary statistics for each of the two groups. You should be able to do this one now. Work it out yourself. Come back when you got an answer and let's check it. Press pause now. So here we're given this two sample sizes, the two means, the standard deviation. It's two independent samples from two different cities, car rental rates in New York and Boston. Well, just as a quick glance, we see that the mean rate in New York is $127.75 a day. In Boston, it's 99.94. Looks like maybe New York might be bigger than Boston on average. It certainly is for the sample. What would be a confidence interval for how much bigger it is? Well, we just run our test. Here I did it on a TI-84. So it's a two-sample T interval. It's not a hypothesis test. It's a confidence interval. Everything is just done from statistics this time, so you just choose stats. We type in our numbers for the first one. X bar is 127.75. That's the average of our sample. 15.83. That's our standard deviation for a sample. 16 is our sample size. That's for group 1, which is New York. Do the same thing for group 2, which is Boston here. Go on down. Confidence level is 0.96. That's given. Choose no for pooled. Calculate. And there's your interval. So we have this is between $17.76 and $37.86 is the difference in price in New York. New York is that much higher than Boston, according to this particular data. So here's the same thing worked out on a TI Inspire, and I think you can see the setup there, and you can see that it gives you the same kind of information. So now it's time to work through problems 31 on the homework set, work 30 and 31 after watching this video. And if you're not caught up, this is a good time to get caught up all the way to that point. We'll move on to hypothesis testing with a t-distribution next.